Okay, so what I'd like to do is to go over this code that we'll use throughout the semester to implement various things. In the assignment that is coming up, we're going to use this code to analyze a 3D truss and a 2D truss with temperature effects. The code as is analyzes a 2D truss with external forces. And this is the example that we looked at in class over the last couple of classes. So the code consists of, it's convenient to think of it as the code consisting of 8 sections. There's one section which has to do with input data. We might call it pre-processing. And then there's a setup section. We'll see what that is. And then there's a section that counts and numbers degrees of freedom. There's one section that constructs a local to global map. We'll see what that is. And one that builds the load vector, one that assembles the stiffness matrix, and then solving and post-processing. Post-processing is just looking at outputs of interest. So first, let's start with the input. In this case, it's called 2D truss input. You could replace it with other things. So let's open this file. This itself has a few different parts. The first part has to do with joint coordinates and support conditions. The second part has to do with members, and the third part is the load. And all inputs would have generally the same structure. So the coordinates is basically x and y coordinates. So this is a matrix with two columns. The first column is the x coordinates, and the second column is the y coordinates. So for example, the x coordinate of joint 1 is 0, the y coordinate of joint 1 is 0, the x coordinate of joint 2 is 6, and the y coordinate is 0, and so on. It's multiplied by 1,000 here just to convert from meters to millimeters, so that's just a unit conversion. Then we have the boundary conditions section. So 1 means fixed and 0 means free. So in the truss examples we looked at in class, joint 1 was fixed in both directions, so it's 1, 1. Joint 2 was free in the x and fixed in the y, so it's 0, 1, and so on. Next we come to the members. Connectivity is just the two end joints. So for a thing like a truss member or a beam, there would be the connectivity would have two columns. The first column is the first joint, and the second column is the second joint. Later on in finite elements and so on, an element could have 3, 4 nodes. In that case, joints are called nodes, in which case connectivity would have 3 or 4 columns. So the number of columns is equal to the number of joints per member or element. And then for each member, we have an area of cross-section. So there's 1, 2, 3, 4, 5, 6 members and 6 areas of cross-section. And then the modulus of elasticity. For this 2D truss, that's all the properties. And then finally, the load vector has x and y components of load in each joint. And because there's 4 joints, there are 4 rows, and x and y components are 2 columns. If there's, for example, it's a 3D truss, there would be 3 columns, x, y, and z. It says from here we can see that there is a load of 10 kilonewtons at joint number 3. So next we get to the setup section. And this section is, the key here is that this code is written in a way that it'll work in 2D, 3D, and different element types, as we'll see later when we talk about finite elements. So this just goes through the input file and deciphers what kind of problem it is. So number of joints is simply, it sees how many joints there are by looking at the coordinates matrix, by looking at how many rows there are in the coordinates matrix. So let's run this section so that we have that information there. And if we're writing a code for production purposes, we have to check that the input is consistent. So here's an example of how you might do a check like that, that the number of rows in the coordinates matrix must be the same as the number of rows in the boundary conditions matrix. Otherwise, it's inconsistent input. But here we are not going to pursue this much more. We'll assume that the user has specified consistent input. Number of members is number of members. Number of degrees of freedom per joint. Okay, so for a 2D truss, that would be 2. For a 3D truss, that would be 3. For a 2D frame, that would be 3. For a 3D frame, it would be 6, and so on. That's obtained by looking at the boundary conditions matrix. Notice that we're not looking at the coordinates matrix there. We're looking at the boundary conditions matrix because, for example, for a 3D frame, there would only be 3 coordinates per joint, but there would be 6 degrees of freedom per joint. So we have to look at boundary conditions. And then we have number of joints per member. So for frame and truss problems, that will always be 2. Like I said, for finite elements, it could be 3, 4, and so on. And we get that by looking at the number of columns in the connectivity matrix. And then this is number of degrees of freedom per member, which is the number of joints per member times the number of degrees of freedom per joint. So the setup section just, from the input, it deciphers these kinds of things. And that's what makes the program generally applicable. So we can do 2D problems, 3D problems, trusses, frames, finite elements, and so on, with minimal changes in the code because we're sorting these things out here. Next, we come to the section where we're counting and numbering the degrees of freedom. We basically go through in a loop and look at the boundary conditions matrix. And whenever a particular displacement is free, then we increment the number of degrees of freedom by 1 and assign it a new degree of freedom number. Notice also here that we're initializing the degree of freedom number array to a bunch of zeros, and that's just a memory allocation thing. That's always a good idea to do. When we grow an array inside a loop, it's always a good idea to initialize that array before the loop. So let's execute this section, which I do by just doing Control Enter. And if I look at what joint DOF num has at this point, we see how because the 2 degrees of freedom for the first joint are fixed, those aren't numbered. And then for the second joint, the x is free, so it's numbered. The y is not free, so it's not numbered. And then for the third joint, x and y are both free, so they're numbered. And then for the fourth joint, x and y are both free, so they're numbered. And that's basically what this loop does. So now, in this next section, what happens is these joint degrees of freedom numbers are just stacked per member. And that's what this loop does. So what you can do to understand exactly what this loop does is to try to build this array yourself and then cross-check with what the program builds. So let's run this section. And if we look at DOF, we see what has happened. So member 1 goes between joint 1 and joint 2, and we see that joint 1 degrees of freedom are numbered. So joint 1 is 0, 0. Then joint 2 degrees of freedom number are 1 and 0. So we have 1 and 0 here. Let's, for example, look at joint number 5. So joint number 5 goes between joint 3 and joint 2. So we see that the degrees of freedom are for joint 3 and then for joint 2. So that's basically what this loop does. And it uses a bit of tricky MATLAB array indexing functionality. But once you understand what it does, it's easy to look through it. And again, something to note is this count the number degrees of freedom and construct local to global map are all things that most of the time we won't have to interfere with, irrespectively of whether we're doing 2D or 3D problem or whether we're doing different finite elements. These are all, I'm just going over this so we understand what it is. But the the setup section, the count and number, and construct local to global map. These are sections that we normally won't have to interfere. Now, finally, this load vector section, what it does is it takes the input load and stacks it into a form that can be used on the right-hand side of k times u equals p. So if we execute this section and look at what P3 is, we see that in degree of freedom number 2, the degree of freedom number 2 is the x degree of freedom of joint number 3. We have a load of 10, and that's what it is. So this basically just accomplishes that. Now, this assembly is probably the a bit of a tricky section, and here it assembles the stiffness matrix in assignment problem number 1. You wouldn't have to actually interfere with the assembly. What you just have to do is to replace this function that computes the member stiffness matrix with a function that does the corresponding thing for a 3D truss. So it says here get 2D truss stiffness matrix. You would have to call the appropriate thing for 3D truss, and the 2D truss stiffness matrix would produce a 4x4 matrix, and the 3D truss would produce a 6x6 matrix. But that's all taken care of when we did the setup. But in the second assignment, second question in the assignment, where you have to, one way of doing it would also involve assembling the load vector that comes from the thermal forces. And so there might be some interference necessary in this part of the code. So again, it uses some tricky MATLAB array indexing functionality. One thing you can do is to run it line by line, which you can do by setting a breakpoint. Well, we're back. F10 would make it execute the line, but my recording program has some other function for F10, so I can't do F10. But we can do a step, which will go through it. And so if we look at what this mask active DOF is, it's a logical array. So each of these numbers is true or false. And MATLAB has this way of indexing arrays using logical arrays. So for example, let's say I have a vector a vec equals 15, 12, 17, and 3. And if I want to index the third element of this, one way to do that is to say a vec of 3. Another way of doing it is to use a mask with logical variables. So I can say mask equals false, 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 true, false. And I could say a vec of mask, which also gives me the third element of the array. So it turns out here when we're doing matrix assembly that it's helpful to use this logical array. So you can run it line by line like this to figure out exactly what it does. I'll show you one thing, and then so right after executing this line, we're in member number 1, and we can see that if I look at K, we can see that the stiffness matrix of member number 1 has been assembled into this global stiffness matrix. So I'm not getting into the details of how the array indexing works. It's pretty straightforward, and If it's not clear, you can figure out what it does by stepping through it, like I demonstrated. So let's run this. And so we now have the stiffness matrix, which is like this. And then the last step is solving the system of equations, which you notice here that u equals, so we're solving k times u equals p, but the way to do it is doing k backslash p. This is the way to do it in MATLAB. Doing inv of k times p is something that some people do, but it's not a good idea. It's not efficient and it's got other problems. So the way to do it is to do k backslash p, which is the equivalent of doing k inverse p. And then finally, we're just kind of collecting all the displacements and the member forces. So once we run it and we look at the results, the displacements of joints 1, 2, 3, 4 are like this, and then the member forces are like this. And you can look at them and see if they make sense and so on. So with that, I'll conclude this overview of the code. We'll talk about it some in class as well. And hopefully that gives you enough to get started with the coding part of the assignment.